Here is a claim that sounds like an exaggeration. The same join, written identically on the same data on the same cluster, can run tens of times faster. The exact gap depends on data size and cluster configuration. The point is that it is not marginal. Nothing changes but which strategy Spark picks to execute it. Last episode, we watched AQE flip a join strategy mid-job and saw the cost difference labeled as huge. Today, we open that up. 3 strategies, what each one physically does, why the cost difference is real, and how you influence which one runs. A single join expression on the left with 3 arrows leading to 3 different stopwatches on the right, labeled same query, 3 different costs. Our fraud job joins 2 billion swipes to a merchant table with 50 million rows. The question is not which join to write. You write join. The question is what Spark does underneath it. Strategy 1. Broadcast hash join. One side of the join is small enough that Spark can send a complete copy of it to every executor. Every executor now has the full merchant table in memory. When it processes its slice of swipes, it looks up each merchant locally. No data moves, no network, no disk. The swipes never leave the machines they started on. A small merchant table being copied to every executor box, each one then joining locally against its partition of swipes, labeled no movement of the big table. The asymmetry here is worth sitting with. If you have 400 gigabytes of swipes and a merchant table small enough to broadcast, the entire 400 gigabytes stays put. You pay only to distribute the small side, once to every machine. That is a fixed cost regardless of how large your swipes table grows. Broadcast hash join is fast. It is also constrained. Spark will only broadcast a table that fits below a size threshold because sending a table that is too large runs out of executor memory. That threshold is configurable and defaults to 10 megabytes, though AQE can effectively raise it at runtime, which is why last episode's mid-flight flip was possible. A size dial with a threshold line, the small merchant table below it labeled can broadcast, and a large table above it labeled too big, too risky. Strategy 2. Sort merge join. This is the default when neither side is small enough to broadcast. Both sides get shuffled, sorted, and then merged. Let us be precise about what that means physically. First, both the swipes table and the merchant table are shuffled. Every row from each table gets sent to the partition determined by hashing its join key. When this is done, every partition on every executor holds all the swipes rows with certain merchant IDs and all the merchant rows with those same IDs. Then each partition is sorted by key. Then the 2 sorted halves are walked together, matching rows as they go. Both tables being shuffled to matching partitions, then sorted within each partition, then 2 sorted streams being walked together, labeled shuffle both, sort both, merge. The cost is explicit. You shuffled 400 gigabytes of swipes, serialized every row, wrote it to local disk, sent it across the network, read it back, deserialized it, and you did the same to 50 million merchant rows. That is 2 full shuffles before a single join result is produced. Sort merge join handles any size of data on either side. It never runs out of memory in the way a broadcast can. It is correct and robust. It is also the strategy you want to avoid when you have a choice because of those 2 shuffles. 2 large arrows showing 400 gigabytes of swipes and 50 million merchant rows both crossing a network, each labeled 1 full shuffle beside a total cost label. Strategy 3. Shuffle hash join. This one sits between the other 2. One side is shuffled by key, like sort merge, but instead of sorting and merging, Spark builds an in-memory hash table from the smaller shuffled side and probes it with rows from the larger side. No sorting required. It is faster than sort merge when it applies because sorting is expensive and you skip it. But it requires that the smaller side, after shuffling, fits in the memory available to each executor for that partition. If it does not fit, it spills to disk, and at that point, sort merge would have been the better choice. Spark also tends to prefer sort merge by default even when shuffle hash would fit, and this preference is configurable. Shuffle hash join is more opt-in than it might appear. So, pause the video and run through the decision tree yourself because this is worth internalizing. If one side fits below the broadcast threshold, Spark will choose broadcast hash join, and the big table never moves. If neither side fits, Spark defaults to sort merge. Shuffle hash join appears when Spark has confidence the smaller shuffled side fits in executor memory and sorting can be avoided. A decision tree with 3 leaves labeled broadcast hash, sort merge, and shuffle hash with the conditions branching to each. Now, the part that matters most in practice. Spark makes this choice based on estimates. We saw in episode 4 that estimates go wrong, and the consequences here are dramatic. Our swipes table is 400 gigabytes. Our merchant table is 2 gigabytes after loading. If Spark correctly estimates the merchant table is below threshold, or if AQE flips it after seeing the real size, we get a broadcast hash join, and our swipes never move. If Spark incorrectly estimates the merchant table is too large, we get a sort merge join, and we shuffle 400 gigabytes unnecessarily. That gap between shuffling 400 gigabytes and not shuffling it is where the 40 times difference lives. So what can you do when Spark picks wrong? 3 things, in order of preference. First, filter before you join. If the merchant table can be reduced before the join, a table that was too large to broadcast may become small enough. We saw this in episode 4 when filtering active merchants brought 2 gigabytes down to 200 megabytes. The join strategy changed because the data changed, not because we touched the join at all. Second, let AQE do it. If you are on Spark 3.0 or later and AQE is enabled, it will flip the strategy if the real post-filter size falls below the threshold. No intervention needed. This is the case episode 5 described. Third, as a last resort, you can hint to Spark that a broadcast is appropriate. In SQL, you can add a broadcast hint, and in the data frame API, there is a broadcast function you wrap around the smaller table. This forces the strategy regardless of the size estimate. Use hints sparingly. A hint that was correct when you wrote it becomes wrong when data grows, and it overrides AQE. The one case where a hint earns its place is a lookup table that is permanently small and will never grow past the threshold, where you want to avoid the overhead of AQE checking dynamically every run. Hard-coded hints age badly everywhere else. So here's the big picture. Broadcast hash join sends a copy of the small table to every executor. The big table never moves, and it is fast but size limited. Sort merge shuffles both sides, sorts both, merges them, handles any size, and costs 2 full shuffles. Shuffle hash shuffles one side into a hash table, skips sorting, but requires that the shuffled side fits in memory. Spark picks based on estimates. Estimates go wrong, and the strategies differ by enough that a wrong estimate matters. Filter before you join, let AQE catch the rest, and hint only when you have no other option. Next time, skew. One task running for an hour while 499 sit idle. Why it happens, how to find it, and what actually fixes it.